You wake up, the sun crests the horizon, and the shades rise in perfect unison. The temperature is already set to your exact preference, and soft lighting guides you to the kitchen. Behind that seamless morning routine is an immense array of microprocessors. We are talking about enterprise-grade Wi-Fi routers, sophisticated security panels, lighting control modules, and distributed audio-visual processors, all running quietly in the background. Think of these systems as the nervous system of the property. The problem is that the standard utility grid is inherently unstable. Even on a perfectly clear day with no storms in sight, the power flowing into your home is constantly fluctuating. This chart illustrates what everyday power actually looks like. The clean, smooth electrical wave is constantly battered by microsurges, sudden voltage drops, and brief brownouts caused by heavy grid demands. These micro-anomalies force sensitive electronics to constantly compensate for unstable voltage. Over time, this cumulative stress wears down the processors, leading to hardware that eventually locks up or loses its configuration. When an AV system requires a hard reboot or a Wi-Fi network drops without explanation, the hardware is often reacting to the instability of the power it was fed. Then a sudden, severe storm rolls in. The local transformer blows, and the entire neighborhood goes completely dark. The standard response is to rely on an automatic standby generator. The utility drops, the engine fires up, and the house has energy again. But a generator alone leaves critical gaps. First is the transfer delay. It takes several seconds for a generator to recognize an outage and power up. In that dark window, your network drops, the security cameras shut down, and the processors reset. Second is the startup surge. When the generator engages, the HVAC units, refrigerators, and pool pumps all aggressively pull power at the exact same moment. This massive demand can overload the generator or send a damaging surge through the circuits. Finally, generators produce raw energy from a mechanical engine. It is noisy, unconditioned, and highly erratic, far from the precise, stable fuel required by sensitive processors. A generator's exact purpose is to create a massive quantity of backup energy, but it is completely blind to the quality and stability of that energy. This is why the power equation requires a second half, the RoseWater Energy Hub. It physically separates the generation of electricity from the refinement of that electricity. This timeline graph shows its first job, zero transfer time battery backup. When the grid fails, the RoseWater battery instantly feeds the home's critical circuits. There is absolutely no gap, meaning the network and security systems never even realize an outage occurred. Once the generator does start, the system performs continuous power conditioning. As we see here on the graph, it takes the jagged, erratic energy produced by the generator's engine and flattens it into a perfectly smooth, continuous sine wave of clean electricity. It also handles step-by-step load management. Instead of letting every appliance turn on at once, it stages the startup sequence, prioritizing the most important infrastructure so the generator is never overloaded. The generator acts as the raw power source. RoseWater manages, cleans, and protects every volt before it touches your technology. Back inside the house, the storm is still raging. The streaming movie hasn't paused, the internet router hasn't blinked, the cameras are recording, and the climate control is steadily humming. The transition was completely invisible. Hours later, the utility grid is finally repaired, and neighborhood power is restored. Switching back to utility power often causes another barrage of volatile spikes and sags. The energy management system catches those too, shielding the electronics from the messy handover. Peace of mind is the result of an engineered system that keeps your family's technology functioning optimally, regardless of the instability on the utility grid.